So we mentioned last time we were going to start to talk about gear ratios, power transmissions, and things like that. So let's say that you had a larger gear. We might call that a bull gear that has radius 2, and then you have this smaller, what we might call a pinion gear with radius 1, and they're hooked together. And they wouldn't necessarily need to be gears. They could be friction surfaces. We'll talk eventually about what if they're belts or something like that, but it's probably nice to think about them as gears. So if I look at the point where the gears are hooked together and I were to enlarge that, so I've drawn that down there, and you see those gear teeth meshed together, we know that the velocity here, I'll say this is velocity 1, and the velocity here, why don't I call that velocity 2, I know those have to be the same, don't they? If they're not the same, they're going to strip the gear teeth off, aren't they? Okay. So if I know that velocity 1 is equal to velocity 2, I could say that the product of omega 1 times r1 has to be equal to omega 2 times r2, doesn't it? So then if I want to talk about omega 1, I could say that that's equal to, or maybe I'll talk about omega 2. Let's say that I was inputting on omega 1, so I'll talk about omega 2. So omega 2, I could, solving for omega 2, I could say that that's equal to omega 1 times the ratio of R1 divided by R2, where R1 is going to be smaller than R2, so omega 2 is going to be going slower, isn't it? So if we look at a arrangement where we have the input going in on a small gear and the output going out on a large gear, so if this is in and this is out, the speed is reduced. Conversely, the torque is increased. Okay? So when you're driving along and you start to go up a hill in your car and you need to shift down, you shift down, that's going to reduce your speed, but it's going to increase your torque, make it so you can climb to the top, right? If we change this a little bit, let's say that we put the input on a large gear, so that's our input, and we take a small gear as the output, what's that going to do? Well, looking at that ratio, the speed would be increased, that is, whatever input velocity or input revolutions per minute or radians per second would be increased, so the speed would be increased, and the torque would actually be decreased. That's like overdrive, right? You can go quite a bit faster, but you probably don't want to use it to climb a lot of steep hills. Well, we can go back and look at this ratio, this R1 to R2. If we look at that, we could, of course, say that that was diameter 1 to diameter 2, because if you take the diameter and divide it by 2, the 2's would cancel. We could say that this would be equal to circumference 1 divided by circumference 2, right? I mean, that's just a constant between those, but getting from the diameter to the circumference. And the circumference would really be a function of the number of teeth. So we could say the number of gear teeth in 1 divided by the number of gear teeth in 2, couldn't you? So we could look at the ratio as the ratios of the radiuses or the ratios of the diameters, or oftentimes even the tooth count. And the tooth count's kind of nice because I don't have to break out any measurement instruments and try to figure out whether I'm talking about the root radius or the radius at the end of the gear tooth. I just simply count gear teeth and make that ratio work out. I'll be probably next week or the week after, I'll bring a transmission into class and we'll go through this for the different gears and see the power flow through that. And we'll check out the ratios, and we'll do that just by counting the gear teeth. So that should hopefully be a good exercise. One thing about this velocity here, if you're still not buying into this, if you've ever tried to maybe shift a transmission, if you look at transmissions they put in great big trucks, or a transmission that was made before World War II usually, they don't have what's called synchro mesh in them. So a lot of times they can be kind of ornery to shift. and you'll have to do what they call maybe matching the gears. If you look at a lot of the large trucks going down the highway, when they are switching gears as they're going down the highway, they're probably not using their clutch. They're actually matching the gear speeds as they go along. And that's why when you see them downshift, a lot of times they'll rev their engine a little bit as they downshift because they're trying to match those gears. That's a great exercise in this because they're trying to make the gear velocities match each other. If you want to go from second gear to third gear, if you can get the gears going the same speed, get this speed here and that speed there together, you can just slide the gears across one another and right into place. Now, for lighter duty transmissions, more modern transmissions, they put synchro meshes in them so that you're actually not shifting the gears. The gears are actually running all the time. That way you can have a little better gear cut, and we'll see this in the transmissions. It can be a little quieter and things like that. And shifting the synchro meshes is quite a bit easier than trying to shift the gears. But it still becomes a velocity game. If you've ever tried to maybe limp home without a clutch, you can actually shift pretty well without a clutch, but you have to get the gear speeds to work out. Questions on that? So if we see a small input driving a large output, we've got a reduction in speed. We see a large input driving a small output, we have an increase in speed. This can also be done with belts. Probably worth another page here. If you have a chain or a belt, if you take something like this, and we have a belt here, and this is in and this is out, what's the speed going to be doing? The speed is going to be dropping, whereas the torque is going to be increasing, isn't it? Whereas if I change this around, if I have a large pulley driving a small pulley, and this could be a belt or this could be a chain arrangement, and I take this as the input and this as the output, then the speed is going to be increased and the torque is going to be decreased. One thing a little bit different from the gears is you'll notice we have a direction change in here. If I'm driving in on omega 1 as clockwise, omega 2 you could see would be counterclockwise. Whereas if I have the belt arrangement, this omega here, I could say omega in, and this omega out are really the same direction, aren't they? We could still observe the ratio that omega out would be equal to, if I were to put radiuses in here, I could say that this is radius 2 and this has radius 1. Omega out would be what? Radius 1 over radius 2 times omega in. Okay, and they'd both be in the same direction. Now you can actually change that direction. I guess we could talk a little bit about some different cases here. If you have the pulleys a significant distance apart, you're probably not going to do this in like on the front of an engine or something. But in an industrial setting, you can actually put a twist in this and have the belts go like that. And in this case, that would be going that way, and this would be going that way, wouldn't it? Okay. Brings up kind of an interesting case. A lot of performance engines will maybe have a camshaft gear that looks like this and a crank gear that looks like that. There's a 2-to-1 ratio between the crank and the cam on a 4-stroke engine. And they'll have a chain, a timing chain, or a timing belt that goes around that. And if you have a performance engine, a lot of times, if you want to go to higher RPMs, you need to get the valves shut faster. So you put bigger springs on the valves to get them slammed closed faster, which takes more force in the camshaft. So eventually you want to try and go with a gear-driven camshaft. And in industrial engines, they will have gear-driven camshafts. The gear on the camshaft will look like this, and the gear on the crank will look like that, and it will be gear-driven. Now, we couldn't probably just change this to that, could we? Because what's going to happen with the direction? Yeah, if this is going clockwise, this is going counterclockwise, isn't it? Whereas this is going clockwise, and that's going... Oops, I got this... no, I got this messed up here. This is going the same way, isn't it? Whereas these are going opposite directions. So how could I get a gear set up for this one? Yeah, I put an idler, set of idler gears in between them. A lot of times they'll put 2 gears because they can get them to kind of float in there. They'll put a couple gears in there like that. And in that case, if this one's going clockwise, this one's going counterclockwise, and then this one's going back to clockwise. Okay. So if you really want a lot of strength, you put square cut gears and it'd be extremely noisy, but then people would hear you coming, and I think that's probably part of the mystique there too. So, okay. Questions with that? So if you do work in power transmission and whatnot, you'll do a lot more of this, but this is some pretty basic stuff. Let's apply this to a problem then. Let's say we've got a hoisting rig here. We're trying to we're lifting this some sort of a load, and it was sitting down here on the ground, and at 4 feet we've lifted it 4 feet, and it's accelerated with constant acceleration from rest. And at this point here, a snapshot in time, it has a velocity of 3 feet per second. And we'd like to find the acceleration of this point C out here on the drum that the cable's being wrapped around. And we'd like to find the angular velocity of the pinion gear A and the angular acceleration of this pinion gear A. So apparently there's this gear B here, this gear B, that's engaging with the pinion gear A, and gear B is apparently probably welded. Maybe they've got some big holes here and they have welded this gear, this larger pinion gear B, to the drum C that the cable's actually wrapping around. Okay, so they've made it like that. So the important thing to think about with B and C is I've got them welded together. So if we were to look at the angular velocity of B and the angular velocity of C, or for that matter, the angular acceleration of B and the angular acceleration of C, what could we say about those? It's one rigid body. They're bolted or welded together. They'd have to be the same, wouldn't they? Okay. So let's see if we can go through this problem then. I guess for clarity's sake, the diameter, the symbol there, the phi is the diameter symbol. So the diameter of the small pinion gear is 12 inches. The diameter of the larger drum that the cable's wrapping around is 48 inches. And the diameter of that bull gear B is 36 inches. So we should be able to come up with some stuff here. We could say that V is equal to V naught. I guess I'd have to say V naught, or V squared is equal to V naught squared plus 2AS if I have constant acceleration, which I do. So I can say then, if this is equal to 0 starting from rest, that the velocity V is equal to the square root of 2 times A times S. Is that right? So I could solve for the acceleration. The acceleration is going to be equal to the velocity squared divided by 2 times S. So that would be the acceleration here, right? Okay, maybe I should use a double arrow since I'm talking about acceleration. So up at C, how would that relate to C? Wouldn't that actually be the tangential acceleration at C? I mean, unless that cable's got a whole bunch of slack in it or something, the acceleration that I found of this load would have to be the acceleration at C, wouldn't it? Okay, so I should be able to go through that. I can say that that's the velocity squared divided by 2 times the distance S. And what do we have there? We've got 3 squared, because I got 3 feet per second, divided by 2 times 4 feet, that distance that it's gone through, which turns out to be 1 1/8, or 1.125 feet per second squared. So that's the tangential acceleration at C. This says the acceleration at C, so presumably I need the magnitude, so I need to get the normal acceleration at C. I could say that the normal acceleration at C is equal to what? And probably our old friend V squared over rho would work, wouldn't it? Is there a velocity at C? Absolutely, it's tangential. It's going to be in the same direction as the tangential acceleration. And again, if the weight is, or the load is at 3 feet per second, unless there's a whole bunch of slack in this cable, or the cable is stretching tremendously, this would have the same velocity, wouldn't it? So I could say that I have 3 squared divided by, what's our radius of curvature? It's curving around that point there, so I need to find that distance, which is what? 2 feet, half of 48 inches, half of 4 feet. And I better put it in feet, so let me say that it's 24 divided by 12, because I want to get that in feet. So this number turns out to be equal to 4.5 feet per second squared. So we could get then that the acceleration of c is equal to the square root. I just square each of those components. 1.125 squared plus 4.5 squared is equal to 4.64 feet per second squared. So that's the acceleration of c. Nothing new there. Well, let's go to the next part of the problem. Let's look for the angular velocity of A and the angular acceleration of A. So I could say that, let's see, omega b, could I say that omega b, which we know is equal to omega c, which is going to be equal to what? We know that v is equal to omega times r, right? So omega in general is equal to v over r, isn't it? Just a little general equation up there. So I could say then that we have what? The velocity divided by r. So what's my velocity at c? 3, isn't it? What's my radius of curvature, or r? 2 feet, yeah, 24 divided by 12 to get that in feet. So this turns out to be 1.5 radians per second. Okay. Now that's the angular rate of B or C, either one. They're all one piece. And but before I try and find omega A, let me deal with the acceleration. Let me talk about the acceleration of B, which should be equal to the acceleration of c, which is going to be equal to what? If I put another general box up here, what do we say that the acceleration in the tangential direction is equal to? Alpha times r, isn't it? Okay, so we could talk about alpha being equal to the acceleration divided by r, right? Okay, so I'm going to take my acceleration in the tangential direction and I'm going to divide that by r. What was my acceleration in the tangential? 1.125? Right there. So 1.125 divided by the radius, which is again 24 over 12, which I end up with, is that right? 0.563 radians per second. So if you're interested in the angular acceleration of B or C, we'd be done. We're not interested in B or C, but we want A. So we have to do one final step in this thing. So I know that omega A is equal to what? Should be equal to omega B times the ratio of R sub B divided by R sub A. Is that right? I mean, that would have come from omega A times RA is equal to omega B times RB, right? Recognizing that on this picture here, if we're not going to tear the teeth off of that, we go on the same way, right? I mean, when someone's not doing a good job shifting, you hear the gears grinding. That's them trying to tear the teeth off because they're not going the same speed, right? Okay, so we've got that. So we can say then that this is equal to omega B, which we have here, 1.5, times then what's the radius of B? That was, if we look at the radius of B, half of 36, whereas the radius of A is half of 12. Now, if I just do this, if I say 36 over 12, what do you think of that? Is that bad? It's actually going to work, isn't it? It's the same ratio, okay? Because whatever units I have here, I have the same units in the top. So whether I divide this thing by 1.5 and a half, or whether I divide by 36 over 12, should be the same, shouldn't it? Okay. So this turns out to be what? 3 times 1.5 gives me 4.5 radians per second. So that would be A. A should have to be going faster, shouldn't it? And indeed it is. So let's do this for then alpha A, which is going to be alpha B times R sub B over R sub A. And I guess maybe I should put a note here for people that go and look at this later. R sub B over R sub A is equal to diameter B over diameter A, which for completeness sake would be circumference B over circumference A, which in a lot of practical senses we would use the number of teeth for B divided by the number of teeth for A. Is that right? All of those would work, so just we'll pick one that's convenient for us. This was convenient, so that's what I used. So here I'm going to have 0.563. Now multiply again by 36 over 12. And you can use 1.5 over a half if you're more comfortable with that. That's fine. This turns out to be 1.69 radians per second squared. So the angular acceleration and the angular velocity of A is quite a bit larger, which makes sense. We are going from a small pulley or gear driving a large one, aren't we? We would expect the speed to drop down significantly, the speed of this one have to be a lot higher. If I were to look at the speed here, this would be very large in comparison to the speed there. Questions with that? Yes?
Should the
let's see. Oh, up here, yes. Alpha B and alpha C should be this squared. Is that what you're referring to? You are correct. Radians per second squared. Thank you. Other questions? Okay, so you've got some homework problems with this. I always think that these are kind of fun problems, so you can have at them.